Welcome to Module 4 of the course Architectural Gap-Driven Justification Part 2. In this section, we'll focus on architectural gap-driven justification, the reasoning behind controls that address weaknesses or missing patterns in enterprise design. Unlike threat-driven justification, which maps to adversary tactics, this approach ensures our architectures are defensible, consistent, and resilient. We'll use ISAUnited's frameworks and methodologies to identify and close architectural gaps. Architectural gap-driven justification. Architectural gap-driven justification is about identifying where a system's design is missing defensible patterns or where ambiguity creates risk. Controls here are justified not because of a specific adversary technique, but because the architecture itself demands reinforcement. These controls are always tied back to the Defensible 10 standards, both parent and substandards, so that they remain consistent, measurable, and defensible. ISAUnited frameworks for architectural justification. To ensure consistency, ISAUnited has developed and adopted advanced frameworks for architectural justification. The ISAUnited Defensible Architecture, IDA, provides a methodology for anchoring security controls at the architectural level. Cybersecurity Design Models, CDMs, are created by architects to analyze network or solution diagrams from the outside in or by following data flows. And Cybersecurity Engineering Concepts, CECs, guide engineers during their build planning to review components, systems, and systems of systems, examining their integrations, encryption, and associations to identify control gaps or improvements. Using CDMs for control identification, architects. For architects, the process often begins with Cybersecurity Design Models, or CDMs. Reviewing networking or solution architecture diagrams, architects can apply methods such as the outside-in approach, analyzing from the perimeter inward, or the follow-the-data model, which tracks how information moves across systems. These models help identify where controls are missing or weak, and map them to the appropriate D10S standards for defensibility. Using CECs for control identification engineers. For engineers, the focus shifts to Cybersecurity Engineering Concepts, or CECs. Engineers analyze components and their integrations, assess encryption mechanisms, and evaluate how systems interoperate. Looking at systems of systems, engineers can identify resilience gaps and recommend new or improved controls. CECs provide a disciplined, engineering-first way to ensure architectures remain defensible at the component level. Correlating to Defensible 10 standards, D10S. Whether through CDMs or CECs, the findings must always map back to ISAUnited's Defensible 10 standards. Parent standards outline the big-picture domains, such as network security or application security, while substandards drill down into specific measures, including VLAN segmentation, API gateways, or encryption. By mapping architectural gaps to D10S, practitioners ensure that identified controls are consistent, defensible, and auditable. Module 4, Recap and Transition. To recap, Module 4 covered architectural gap-driven justification, controls justified by defensible patterns and architectural consistency. ISAUnited's frameworks, IDA, CDMs, and CECs, provide structured methods for identifying and closing gaps. For architects, CDMs highlight missing controls in diagrams using outside-in and follow-the-data models. For engineers, CECs reveal weaknesses at the component and systems of systems level. All findings align with the Defensible 10 standards, ensuring that controls remain consistent and defensible. Next, we'll move into Module 5, where we apply the RACI model to clarify roles, responsibilities, and continuous improvement.